Okay, everybody. Welcome to this year's Heyting Day. The event today is organized in honor of Jaap van Oosten's retirement. So usually the Heyting Day is dedicated to 50 years or 100 years of the anniversary of an important paper in logic. So in 2019 it was Frege's Der Gedanke, and in 2022 it was Wittgenstein's Tractatus. So this year we diverge from this pattern. So, well, everybody knows that Luther or Goethe or Bertolt Brecht or Mark Rutte said, jede Konsequenz führt zum Teufel. So, but on the other hand, maybe we can construct a connection with a great paper, namely Kleine's great paper, The Interpretation of Intuitionistic Number Theory of 1945. Okay, that's 80 years and not 50 or 100, but it's still a worthy number. Okay, so now after two philosophical Heyting days, so this is a more logic day. So the real stuff. So even if there's still a philosophical component. So today's lectures, as everybody has seen, are centered on themes in Jaap's work. So first we will have Andy Pitts, and he will tell us an extremely gripping story, namely how a puzzle concerning the truth value object of higher order intuitionistic logic led to a completely surprising discovery in intuitionistic propositional logic. Then Andre Bauer will explain to us about the effective topos, so that's the world in which computability is built into the very fabric of the universe. And he will explain that this topos is indeed a good place to do recursion theory. Yeah, so that seems to be completely self-evident. Of course, you designed it for it, and then it does what it is supposed to do. But my experience is that most of the time that isn't true. So, we are going to hear good news from Andre. So then we have Bas Terwijn, who will explain the effective topos. So that's. Sorry, that's not right. Who will explain partial combinatory algebras. So they are the fundamental objects that also play an important role in the construction of toposes. And then, of course, Jaap van Oosten. Yeah, so in Dutch we have the word feestvarken. But it's untranslatable. It would be the festive pig. But that doesn't feel right. He will give this year's Heyting lecture, and he will explain to us how the information flow is not just from categories to logic, but also in the other direction. So you will hear more about Jaap's work and about Jaap himself in Benno's introduction to Jaap. Okay, before giving the floor to the first speaker, I want to share some Heyting news with you. That's surprising. Most of the years we do not have specific Heyting news, but this year we have. In 1955, it turns out that before he published his famous book, Intuitionism and Introduction, he wrote an article in French, Les études philosophiques. So that's about intuitionistic logic explained to philosophers. And it has the title La conception intuitionniste de la logique. So that paper starts with the opposition between logique de l'être and logique du savoir. And so their intuitionistic logic is presented as the logic of knowing. So that's interesting because it differs really from what Heyting is saying later in his famous book. And so the news is that a group of 4 logicians, Philippe Balbiani, Dick de Jong, and Hans van Ditmars, and Yang Ying Wang, are preparing a translation of this French paper in English and in Chinese, and very soon this will be out. So stay tuned to see that translation come out. Okay, that's all I wanted to say. And so now, without further ado, we move to the first lecture, which will be chaired by Rosalie.
Thank you. So it's my great pleasure to introduce our first speaker, Andrew Pitts. Now, I don't think he needs an introduction, but I'm going to give it anyway, because I like that. So, yes, I know, but I'm in charge. No, so Andrew Pitts started out as a PhD student under Peter Johnson to work on the applications of category theory in logic and the foundations of mathematics. And then later, with a shift of departments in the late 1980s, he started to work again on applications of category theory, but then in the field of the semantics of programming languages. And as someone puts it very nicely, I read it somewhere, that he changed from being surrounded by mathematicians to being surrounded by computer scientists. And with a wealth of publications, supervision of PhD students and other students, he has been has been a great influence in the field. But I want to take the opportunity to also, on a personal note, say something. Because Albert alluded to that already, that in 1992, Pitts published a paper that he's also going to talk about. And something happened that sometimes happens in research, and that is that this paper, besides the expected impact on the field where it was meant for, also suddenly it occurred that it had consequences in other fields in logic. And in fact, many people in the Netherlands have worked on this property that, so to say, emerged from this paper for many years. And also very recently, in the last years, some colleagues who are present here and I have worked on the development of a certain technique in proof theory where Pitts' paper was really instrumental. So I'm very grateful for that. And with this word of personal thanks, I want to give the floor to you.
Thank you. Very good. Well, thank you very much. I'm just going to, before I start, do a sound check. So if I stand around here, you're hearing me okay? I know there's one member of the audience who can hear me because of this, but okay. So I'll try not to wander too much, but if I do, shout at me. Okay, so, well, first of all, thank you very much to Albert and Benno for, first of all, giving me the opportunity to be in this place, this august institution that I've not been in before. So it's fascinating to be here. And to speak at a Heyting day is a great honour for me, because Heyting, in one way or another, has been quite an influence on things I've done. I don't know whether it's true. Did Brouwer say that he thought that Heyting's formalisation was sterile? Well, I'm a kind of person who likes syntax and rules and formalism. So my grip on intuitionism is very much coming from the point of view of formal systems rather than any philosophical point of view. And the thesis of this talk is not a very controversial one. The thesis is that if we're going to study models of intuitionism and computability, so that's the subtitle of this day, as it were, then the mathematical theory of categories is a crucial technological tool for doing that. So, you know, that's we'll see a bit of that in this talk, but it's sort of evident in the title of Jaap's book, for example, on realizability, which has the word categorical in it. And I must say, it's very nice to be here to celebrate this young man, not so young man, and his career. Yes, so what I am aiming to do So I want to sort of basically make some observations about the role of category theory in logic and also the influence of logic on category theory. And the other thing I want to do is, as Rosalie intimated, is that I want to recall for you what's an open problem to do with higher order intuitionistic logic and the bit of category theory that has to do with things called toposes. I was thinking about this. It's funny. Since doing the work I'll tell you a little bit about in the middle of this talk, which was sort of in the early 90s, I don't think I've actually, in fact, ever given a talk since then about this particular topic. So it's quite a pleasure to be able to do that. But I do have an ulterior motive, which is that I really would like to have the open question that I'll tell you about settled. I don't think at the moment we know what the answer to it is. It's maybe not the world's most important question, but it's kind of embarrassing that we don't know what the answer is. And I'm sort of hoping that some young person in the audience will either come to me at the end of the talk and say, well, surely it's just X, Y, and Z, or at least go away and solve it very quickly, because I think it's probably quite solvable. It's just that I and a few other people haven't managed to actually do that. The other thing I'll aim to do is I was told not to be too technical, so I'm not going to be too technical in this talk. And so I apologise to the people I can see in the audience who know far more about most of the things that I'm talking about. But I've learnt over the years that you can never be too simple, that even, you gratify the people who think that they know what the stuff is anyway, and the people who don't appreciate not being told things that they don't understand too much. Of course, my idea of what being not too technical is might not correspond to yours, but we'll see. So let's begin at the beginning, right? So I can't, as it were, really, I'm not going to assume that you know very much category theory, and I'm not really going to even tell you what it is, but we should have at least some attempt to say what kind of thing it is. And maybe, a good way of thinking about it is in terms of what the mathematician in the street would use in the way of foundations or language when describing structures that they were interested in studying. And they would probably use some sort of set theoretic language. So a mathematical structure of some kind would be described in terms of what kind of elements it has and the relations and the functions between the elements that are relevant to that kind of structure. So category theory approaches mathematical structures in a apparently quite abstract way, that the only way that you can really talk about a structure is by saying things about how structures transform between themselves. So category theorists call the transformations morphisms rather than transformations. To know a structure, you have to know what kind of morphisms go into that structure or what come out of them and how the morphisms compose. And at base, that's the only means of expression that you have in terms of those simple concepts. So it seems on the face of it that you wouldn't be able to really say anything very much or very interesting at that level of abstraction. But it turns out, as we know, that category theory is amazingly expressive in some ways, starting with that base language, which is transform theoretic rather than element theoretic, as it were. And I'm going to look at two places where it's been useful to take that kind of category theoretic point of view. So one is the use of the category theoretic notion of adjunction in proof theory, and the other will be to look at particular sorts of categories called toposes in relation to models of intuitionistic higher order logic. So let's start with adjunctions and proof theory. So adjointness and adjunctions, I think I'm right in saying that the original paper on category theory, so by Eilenberg and MacLean, 1945, I guess it appeared, didn't mention the notion of adjoint, if I remember correctly. I think it's probably its first appearance in print was 10 or so years later. Daniel Kahn had a paper in 1958 about adjunctions. But roll on to now, and I think most people would agree that the notion of adjunction is the key concept in category theory. So the notion of category and functor and natural transformation exists so that you can explain what an adjunction is, because they occur everywhere and explain lots of disparate, apparently different things in terms of this single notion. So again, I'm not going to attempt to define what an adjunction is in generality, but I thought at least we could see the definition in the simple special case where we're just looking at categories which have at most one morphism between any two things, so partially ordered sets. So if I have two posets P and Q and a monotone, so an order-preserving function between them, okay, then I would say that, I'm getting my buttons mixed up, there we are. So I'd say that if you've got some element of the second poset Q, the monotone function has a right adjoint at that element Y. If you can find some element back in P, so let's call it G of Y, okay, with this property, so that f of x is less than or equal in Q to Y, if and only if x is less than or equal to this element GY. Okay. So if that happens for all x, then I'd say that this element gy was the value of the right adjoint to the monotone function f at y. And if that exists for every y, then we say that f has a right adjoint, so some function g going back from q to p. And this property here uniquely determines g of y for a given y, and so if you've got one for each y, then you get a uniquely determined function extensionally. So the right adjoint, if it exists, is uniquely determined by f, and it's again a monotone function. That's a right adjoint, so why right? Because you see that f appears on the left of the less than or equal, and g on the right of it. So G is the right adjoint to F. And the dual concept of a left adjoint would be where you just use opposite orderings. Okay, so it's just dually, you can have left adjoints. So Bill Lauvier and Jim Lambeck, sadly neither of them still with us, I guess in the late 60s and early 70s, observed that very many logical constructs can actually be characterized by being either left or right adjoint to some other construct that you already have. Usually maybe with some extra condition. I'm going to, in most of this talk, gloss over that aspect, but you want sort of the adjoint to not just exist, but to be stable under various kinds of substitution for it to work out properly. But the point is that, and what's good about this adjoint characterization of logical constructs is this uniqueness aspect. If you know that a construct is characterized as an adjoint, then you know that it's uniquely determined, okay? So if you're in some kind of logic and you're looking for a doodah that you know is supposed to be a right adjoint to something, then there's only going to be, you know, it either exists or it doesn't. There won't be two different choices of such a thing. And that's philosophically and practically quite a useful thing to know. And, you know, the prime non-example of that would be most modal operators are not characterizable as adjoints. So that, at least to my mind, gives modal logic a somewhat, why it feels different to me, I'd say somewhat distasteful to me, even if you were to press me. But I don't really mean that, of course. But that is an important example of something that doesn't fall into this orbit. But many basic logical constructs are characterizable. Maybe a surprisingly large number of them. And this was the observation that these guys made back then. So one example, right? I mean, if we take the notion of universal quantification, right, in various different situations, but let's look at it in Heyting's intuitionistic predicate logic. Okay, so one way of characterizing what the universal quantifier is, right, is that so I suppose I've got two formulas in intuitionistic predicate logic, and the left-hand one doesn't involve the variable x. Okay, and so I'll use a turnstile symbol for entailment in this logic. So if phi entails psi, okay, and it's the case that this thing doesn't involve x, then it's going to be the case that phi entails for all x psi, and vice versa. So we get this if and only if characterization of universal quantification. So this is an example of an adjunction, right? So what's the f? What's the monotone function? It's kind of invisible, right? So in this case, it's just the weakening operation. So if you take all the formulas in some variables y, quotiented by intuitionistic entailment, those are included in all the formulas in y and an extra variable x. And that's what, so that's f is being applied there, that weakening function is being applied to this formula. It's just that it's a no-op, as it were, as far as the notation goes. So you don't see the f on that side. And the g is this for all x that is restricting formulas to things that don't involve x. And g is on the right of the turnstile and f is on the left of the turnstile. And you've got this if and only if. And their monotone, weakening is obviously monotone for entailment. And so we get for all cropping up as an instance of a right adjoint, in this case to the weakening operation. Okay, so let's look at that now, not in predicate logic, where these phis and psis are formulas built up from the usual propositional connectives and quantifiers, okay? But let's look at that now in the case of propositional logic, okay? So now I want to take formulas which are built up from variables that stand for unknown propositions, things of sort omega, as I'll say later, okay, using just true and false and conjunction and disjunction and implication. But there are no quantifiers or anything like that, okay, so they're just first order propositional formulae in the usual logical connectives. And I'm looking at the modulo entailment in intuitionistic logic, okay. So we could ask, you know, if I've got an entailment like this, so phi implies psi, where phi involves some variables q and psi involves the same things and one other extra thing p, could I find a formula to replace the question mark by so that you get an if and only if like this? I would say up until 1991, the answer, if you'd asked anybody, they would say, no, of course not. I mean, it's entirely unlikely because you have very limited means of expression. You just, the formulas have to be built up propositionally, right? There are no quantifiers or anything. So how on earth could it be that you could have something like that? So the surprising thing was that there do exist first order propositional formulae. So I'll call them A sub p for all, and there's a dual E sub p for exist. So that would be the left adjoint to weakening. The A sub p would be giving the right adjoint. But the A there is a formula that fills in the question mark for all possible choices of psi and p and the extra variables q that makes this true. And I would emphasize this thing is constructed from the variables using true and false and or and implies, but nothing else. So that's quite a surprising fact, actually. Why is it surprising? Well, first of all, if you think if we were doing classical logic, so Boolean logic, not Heyting logic, okay, then this is not a very tricky problem. That's because in classical logic, a variable p can't be, you can't tell p from p equals true or p equals false. No, the formula p if and only if true or p if and only if false is the same thing as p up to provability. So everything internally is either true or false, and so we can get the quantifiers just by taking our formula psi and substituting for the variable p first true and then false and taking the disjunction, and that would give us something which classically fits in here, and for the exist would be the same thing but with a conjunction. So in classical logic certainly these things exist, but intuitionistic logic is far more complicated than classical logic. I mean, we don't know, I would say in general, a huge amount about what this thing looks like as an algebra or as a lattice. The formulas of first order formulas in propositional logic modulo intuitionistic provability. I mean, what do we do know? We know that up to entailment there are infinitely many different formulae as long as you've got at least one variable around. And for two or more variables, we don't have a very great hold over what the explicit structure of the lattice of formulae modulo provability is. And in particular, right here, we're asking with this if and only if, there are going to be infinitely many different Q. If I just go back a slide here, we're asking with this property here, this A sub P has got to be the biggest thing, right? The biggest thing with the property that it doesn't involve the letter P and is entailed by Q. So there will be infinitely many different formulae in general that don't involve the letter P and lie above Q in the entailment relation. And you know, the biggest one would be like the disjunction of all of them, but that's an infinite disjunction, so that's not going to be a formula in the logic anymore. So it's not at all clear why these things should exist. But they do. They do. I proved it using proof theory, and it's actually quite a good sort of sub-story about how that happened. You'll see in a moment why I was trying to prove this. I wasn't particularly interested in proving this result. I was interested in disproving it. I'll tell you why in a moment. And I tried to disprove it. I tried to come up with a particular first-order propositional formula for which the A sub P of it doesn't exist. Okay, and couldn't. And it was only later, probably about 1991 or something, I was sitting in a seminar that the late Roy Deacock was giving, where he was telling me and the audience about a particular presentation of Gensen sequent calculus for intuitionistic logic, where you expand the number of rules for implication so that you get a presentation of the sequent calculus with the pretty property that there's a well-founded measure of size on the sequence, which goes strictly down from conclusion to hypotheses, which isn't the case for the usual presentation. So this is something that Roy Deacock discovered independently. Hüttelmeier discovered it, but it turns out both of them had, were in arrears of the Russian proof theory school of some decades before. But just they didn't know about it. But Borodyev had basically the same system. So it's a very nice presentation of sequent calculus for intuitionistic propositional logic. So it immediately shows you that the thing's decidable because you can't grow your proof trees up more than finitely because of this well-founded ordering. But the cool thing for me was that I realized, actually during the seminar, it suddenly struck me that probably the work I'd done on trying to work out what on earth these things could be with a view to seeing that they couldn't be, actually could be proved to exist by doing a kind of rather boring enumeration of possibilities using this proof system to make sure that the algorithm terminates. So there is indeed a constructive proof of the existence of these things, so that they're computable. If you give me a formula in propositional logic, we can compute its A sub P, as it were. At least in principle we can. So I just flash up what the algorithm looks like. It's pretty disgusting. And yeah, I mean, don't even sort of look at it. But it's basically what one is going through is that you're looking at the sequence, you're looking at the formulas in them, and you're, depending on their structure, throwing in instances of the thing that you're constructing at previous stages, and you're doing this using the well-founded ordering on the multisets of formulae, so you know that the process is eventually going to terminate, and the thing that you're interested in then comes out basically the A is a big but finite disjunction of things you've already constructed, and the E is a big but finite conjunction of things. So there's actually been some recent work by Sam van Gool and Ferret. So they've improved the algorithm. I mean, it's still probably, I don't know what the complexity of the algorithm is. I'm sure it's super bad in general. But they've done some work, kind of optimizing it a bit, and also checking that I was right, which is always reassuring. So they formalised the algorithm and the proof of correctness. I think, if I remember it, I think they did it in Coq. But it's good. It's really good to have that. And in the process of doing that, all this sort of working with theorem-proving systems, it's not just checking that the thing that you thought was true is true. You generally, in the process of formalisation, come up with better things as well. And they've certainly come up with a better algorithm. But another very interesting development that took place a few years after I published that results, is about 95 or so, is that, I mean, in a sense, you don't get a feel really for, it's just that this process happens to work, and it's kind of amazing that it does, but you don't come out of that knowing why it works, really. Whereas Silvio Gallardi and the late Marek Zawodowski, they produced a model theoretic proof. So it's not a constructive proof, so that's bad, but it gives you, you know, through infinitary means, a deeper insight, I think, into what's going on with this result. So they prove this theorem about the existence of these formulae, basically using a duality between, so that I'll come back to Heyting algebras in a moment, but Heyting algebras are sort of the algebraic version of intuitionistic propositional logic. And they developed a duality between Heyting algebras and certain kinds of sheaves with a kind of game theoretic structure attached to them. And we're able to use that to get a model theoretic proof of this result. A bit later, Saint-Vangoul and Reggio have, I think, a slightly cleaner version. So they use the known duality between Heyting algebras and certain ordered topological spaces that are called Asakya spaces now, and the duality is these days called Asakya duality. And it's probably slightly kind of oversimplifying things, but roughly speaking, why my result is true is because if you start with an extension of Heyting algebras, so a morphism of Heyting algebras, where you can see that the top thing is finitely presented over the bottom thing, and you flip it over the Asakya duality, you can show that that actually becomes an open continuous map. And so the existence of the left and right adjoints then follows from the openness. So that's, I think, is sort of the most conceptual way of seeing it. I mean, of course, it doesn't explain, as it were, why it happens. It's just a marvellous thing that it does happen. And you still have to do some work, even if you're working with this duality theory, in order to see that it works. Another way of thinking about this is in terms of interpolation. So I mentioned that because it sort of turned out to be probably, you know, in some ways a better way of thinking about it. So you probably know, you know, Craig interpolation. If we were looking at the Craig interpolation theorem for this intuitionistic propositional logic, it would say that, you know, if you've got one formula entailing another, and the first one involves some variables and this involves some other variables, and there's a variable in common, then Craig interpolation says that we can find a formula that just involves the common variable that sits between the two with the entailment relation. Okay, so that's you know, an old theorem that's true in many systems, certainly true in this kind of logic. So you can see that the result that I proved is actually showing you that amongst all the possible interpolants that you have, there's actually a smallest one, which is given by existential quantification interpreted in intuitionistic propositional logic, and a biggest one given by this interpretation of universal. So not I, but others attach the name uniform interpolation to this property of having least and greatest interpolants. And since 1992, many people, possibly among them, have looked at whether this uniform interpolation holds in other kinds of logic. So you could say that many modal logics do satisfy uniform interpolation, but some don't. I mean, so S4, for example, Ghilardi and Zawodowski in 95, they proved that S4 doesn't have this property. So some do, some don't. Okay. Well, back in the early 90s, I certainly hoped that intuitionistic propositional logic didn't have the uniform interpolation property as it's now called. Okay, and I want to spend the rest of this lecture explaining to you why it was that I thought, why it would have served my purpose to show that this property does not hold of IPL. So to do so, we're going to talk about toposes and models of intuitionistic higher order logic. Okay, so first of all, let me just say what I mean by intuitionistic higher order logic. Okay, so now we're going to do not first order predicate calculus, we're not going to do propositional logic, we're going to do the higher order version of predicate calculus. Okay, so we'll have variables, each variable will have a flavor, a sort. Okay, and in first order logic you might just have some basic sorts, like your variables might be ranging over things that you thought were numbers or something like that. So in higher order logic we actually have a structure on the sorts as well as some ground sorts. We have, so I'll formulate it in terms of being able to take the power sort of a finite sequence of sorts. So you should think of a variable of this sort as somehow denoting something which is going to be a subset of the Cartesian product of the things denoted by x1 through xn. So we have that structure on sorts, and then for formulas we can just very simply just use implication and universal quantification over sorted variables. Okay, formulas built up using those two constructs just from atomic formulas that are asserting membership relations. So our atomic says that that this sequence of variables which has sorts x1 through xn belongs to the variable that denotes an element of this power sort p of x1 through xn. So those are the atomic formula, and then we'll build up implications and universal quantifications. And rather marvelously, but somewhat impredicatively, you don't need to put in true or false or and or if and only if or exist or even equality. Those are all definable from implication and for all, starting with membership in this higher order logic. I mean, of course, you do have to have something that says something about power sorts. So we'd have say a comprehension axiom that's asserting the existence of elements of power sorts for comprehending on some formula phi and looking at all those things. So y collects together those things, x's that satisfy the formula phi. And of course, if you've got a ground sort with, say, trying to do natural numbers or something, you'd throw in some axioms for that, some infinity axioms. But it's a very simple but expressive system, right? And I purposely, there are different ways you can formulate higher order logic, and I've chosen the one that's furthest away from the category theoretic modelling. Okay, so on the category theoretic side, we now know, through decades of interesting work, that there's a very close correspondence between models of that kind of intuitionistic higher order logic and certain kinds of category. So again, I can't really give you the precise definition, but I kind of sketch what it is. So a category consists of objects and morphisms, and you can compose the morphisms together and you have identities. And then you can express various adjointness conditions using those means of expression. So a topos is a category where you have things called finite limits and you have power objects. So the finite limits are just adjoint characterizations of things like Cartesian product, functions being injective, inverse image of a subset along a function. So these are all things that are expressed in terms of so-called finite limits and are indeed things that are characterized by being adjoint to various things that you already have. And then a little bit more especially, we have power objects. So again, I won't give you the definition, but it's roughly speaking an adjoint characterization of the notion of power set and comprehension in terms of an adjointness property. So it's also a very simple notion at base, somewhat different looking from what we had here. Okay, but I mean, obviously there's some connection because of the power objects will obviously be to do with interpreting power sorts, but where do we get the interpretation of implication and for all and things like that? Well, it turns out that the combination of these two things give you a lot more than you thought you might have had. So the history of this is, the prehistory is sort of from the Second World War up until the mid-70s. The work on using various kinds of sheaf theory in order to get results in algebraic topology, algebraic geometry, number theory, culminating in Alexander Grothendieck's notion of what we would now call a Grothendieck topos. So it's a set-valued sheaves on a very generalized notion of topological space. In the sort of second half of the 70s, Bill Levere and Miles Tierney, and many other people as well, realized that you could give an elementary in the sense of a finite tree, kind of essentially algebraic description of categories that should be called toposes. So that Grothendieck's toposes are examples, but there are other special ones that have some good but infinite tree properties. The definition here I've given you of topos is really, I should have said elementary topos, because that's what I'm defining. And it's these guys who discovered the connection with intuitionistic logic and higher order logic and other things besides. Then at the end of the 70s, Martin Hyland, I should say, by the way, that he was also my PhD supervisor as well as Peter Johnson, so I had much richness in the sense of having two supervisors. Don't know how that works out exactly, but lucky me. So Martin was building on previous work by Kreisel and by his supervisor, Robin Gandy, and came up with the notion of realizability toposes, which was at the time extremely surprising because whilst it's the case that we had examples of elementary toposes that weren't Grothendieck toposes, they were, kind of not terribly interesting. Well, I don't know. I mean, that's probably not right to say, but the thing is that realizability toposes are definitely elementary toposes that are not of the kind that Grothendieck was using. They're not Grothendieck toposes, and connected to computability through various notions of realizability expressed in terms of combinatory algebras. So these are all things that in the talks in the rest of this day that we're going to hear far more about, so I'm not going to say any more about them here really, except that I want to just give you a flavour of what the range of these kind of different toposes is like, just in terms of what the different notions of truth are that you get. So let's start with classical truth. So that's usually, you would think of that as a sort of two-valued yes-no Boolean type of truth, right? Well, if we let's take the two values to be, let's have a one-element set. So its one element is star. So there are two subsets. There's nothing and there's the whole thing, okay? So there are two truth values. And, we could explain the meaning of implication by saying, that star realizes that implication if either star realizes the conclusion or it doesn't realize the antecedent. So that would be, the classical explanation of implication in terms of not phi or psi. And the corresponding topos is the classical, is the topos of sets and functions in classical, say, Zermelo-Fraenkel set theory with enough universes. So contrast that, say, with what you might call continuous truth, right? So that's where now the truth values are open subsets of the real line, okay? So a real number realizes an implication by definition if there's some small number epsilon, so that if you're within epsilon of x, then y has the property that whenever it realizes phi, then it realizes psi. Okay, so that's a different notion of why an implication should be true, and the corresponding topos is the one you get by taking the real line with its usual metric topology and looking at set-valued sheaves on it, if you know what those are. Don't worry if you don't. In that's a Grothendieck topos, and the kind of truth that you've got in there is as far as implication goes, is exactly this kind of thing. Then there's what you might call cleanly realizable truth. Okay, so now our truth values are going to be arbitrary sets of numbers, right? And a number realizes an implication if whenever you have a number that realizes the antecedent phi, it should be the case that the nth partial recursive function in some standard enumeration of the partial recursive functions is defined at M and takes its value realizing psi. So to realize this implication, you have to be a partial recursive function that maps realizers of phi to realizers of psi. So that's really, you know, one concrete embodiment of the sort of Heyting, Kolmogorov explanation of the meaning of implication in terms of functionality. And the topos that's overlying this kind of truth is exactly Martin Hyland's effective topos that first appeared in print in the Brouwer Centenary Symposium volume in 1982. And we'll hear in talks later today more about the nature of the effective topos and what you can do in it, so I won't say any more here. But you can see those three notions of truth are all somewhat different looking things. So what do they have in common? So they're all things that arise from toposes, elementary toposes, various kinds. So what kind of notion of truth value does a topos have in general? Okay. Well, I can't answer it. That's not really a very well formulated question. But we can kind of try and pin that down in a somewhat boring way in terms of Heyting algebras. Okay. So a Heyting algebra, you know, is to intuitionistic logic as a Boolean algebra is to classical logic. So it's the algebra, as it were, of truth values in general. You know, in terms of order theory, it's a distributive lattice. So you've got meets and joins, and the meets distribute over the joins. It's bounded, so you have a top element and a bottom element, and you've got you know, what some people will call relative pseudo complements, or you know, better called Heyting implications, I think, right, which are just the Heyting's explanation in terms of order theoretic stuff of what implication in intuitionistic logic means. So if you take some theory in intuitionistic higher order logic, so some constants and some axioms over the basic stuff of intuitionistic higher order logic, quotient by provability, you get a Heyting algebra of sentences, so they're closed formulae with no variables. Modulo provability is going to have the structure of a Heyting algebra. And equivalently, the same thing, you know, is true for toposes. So if you take a topos E and you look at the power object of the list of no things, so that's like the object of truth values, sub-object classifier, as topos theorists call it. And if you look at the equivalent of the sentences would be the global elements of that object in the topos. So this is the set of morphisms from the terminal object into the sub-object classifier. Okay, so that carries naturally the structure of a Heyting algebra, coming from the fact that E models intuitionistic higher order logic. So the answer, one answer to this question here is, well, Heyting algebras. They're all Heyting algebras. Okay, and I suppose a very natural question, right, then is, which Heyting algebras? All of them? Well, the embarrassing thing is, as far as I know, we don't know the answer to this question, right? So this is the open question that I referred to at the beginning. Is every Heyting algebra, does every Heyting algebra crop up in this way as the truth values of some elementary topos? So just an easy first observation is, if you're going to answer this question, you don't have to consider all Heyting algebras. You can just consider free Heyting algebras, because you know, every Heyting algebra is a quotient by a filter of a free Heyting algebra. And in the world of toposes, there's something called a filter power construction. So if you have a filter of truth values, you can form a new topos, and its truth values will be the quotient of the truth values in the previous one by the filter. So it's enough to answer this question just for free Heyting algebras. And I very much, at the time, I don't actually know whether the answer to this question is yes or no now. I kind of beyond caring. Well, no, I care, but I just don't know. But certainly in the 1980s, I thought that probably it would be the case that the free Heyting algebra on countably many generators, to be very specific, is not the Heyting algebra of some topos, and that it should be possible to prove this. And my strategy for proving it is quite straightforward, right? So, I mean, were the free Heyting algebra on X, so X might just be the natural numbers, let's say, were it of the form of the truth values of some topos, the fact that that topos models higher order logic means that the topos is able inside itself to do universal and existential quantification over things. And that has an effect on what you get in the truth values. And it's not hard to see that if this free Heyting algebra is of this form, then actually intuitionistic propositional logic has to satisfy what's now called the uniform interpolation property. And at the time, it seemed highly unlikely that that property would be true. And so I searched and failed to find examples of formulae in intuitionistic propositional logic for which one of these A or E formulae couldn't possibly exist. And I wasn't able to. Roll on to 1992, and then I was able to prove that actually they always do exist. So that's nice, right? But it doesn't answer the question. All it does is to show that this is a failed strategy for resolving the question. Okay, so it doesn't resolve the question, it just shows you that you can't prove it one way or another this way. Okay, even though it's an interesting result, it's nevertheless, from this point of view, somewhat disappointing. What else has happened since then to try and resolve this question? I think the main thing is to do with somebody called Dito Pataraya, who unfortunately died in 2011, so he's no longer with us. But in 2007, he came up with a claim of resolving this question in the positive. In other words, I give him a Heyting algebra, he constructs an elementary topos whose truth values is that Heyting algebra. That's actually the more interesting answer to the question. I mean, we want to resolve the question either way, and no is okay if it's true, right? But it'd be better if the answer were yes, because then we would get a whole slew of maybe interesting, maybe not interesting, but certainly probably new toposes that we didn't know about for given Heyting algebras. So it would be nice if the answer were yes. Dito claimed the answer was yes, and his strategy is it kind of came in two parts. So the first part is that he formulated not exactly the notion of what Peter Johnston and Martin Hyland and I called tripos, a slightly different notion, but it's sort of one situated in algebraic logic, so cylindric algebras and things like that. So he formulated the notion of a higher order cylindric Heyting algebra, or Hotcha, as he called it. And every Hotcha has a Heyting algebra of truth values, okay? And every Hotcha generates a topos in a way that's not dissimilar to the way that every tripos generates a topos, if you happen to know that kind of stuff. So all of this is absolutely fine and okay, and not the same as tripos to topos, but not disconnected from it. Then the second step, which is the difficult one, is that he claimed that he could use Stefano Ghilardi's construction of free Heyting algebras. So Stefano has a paper here in 1992 that presents free Heyting algebras as a filtered colimit of distributive lattices, basically filtering on the implicational complexity of the things in the free Heyting algebra. And Dito claimed that he could use that to construct a Hotcha whose truth values were the given free Heyting algebra. But he never published the details, and as far as I know, people who have looked at it to try and reconstruct what those details were haven't been able to do it. So as far as I'm concerned, this is, I don't know quite how he intended to do it, and I can't see exactly how to do it. But that doesn't mean to say that there isn't some way of doing it this way. It's just that we haven't thought of it. But maybe there's some other completely different approach. Who knows? I'm afraid it's, as far as I know, still open. So, nearly the end of the talk. So my only purpose in giving this talk, really, apart from sort of, socialising category theory, was in the hope that somebody might be sufficiently interested to resolve this question for me. But over and above that, I'd say that, what's the moral of my talk? Well, category theory, über alles, as they say. No. Well, it's certainly a sine qua non for understanding how to link logic to geometry in the sense of sheaf toposes and link it to computation through notions of realizability. And we've known that for, and built up on it over some decades. In the modern era, so sort of, post 2010 or whatever, there's a somewhat different but related kind of thing going on, and that's that people are, from Grothendieck onwards, have been interested in trying to get a better grip on homotopy theory of spaces. Maybe not all topological spaces, maybe some kind of tame space. And higher dimensional category theory has long been known to provide a sort of combinatorial setting in which you can get to grips with that. But higher dimensional category theory, at least as far as I'm concerned, is really a tough subject. So I've got a misquote here. The DS here is Dana Scott, okay? And I'm misquoting him, because actually what he said that sucked is just two category theory. I remember being in a conference where some Australian category theorists were telling him about some stuff, and he just said, "Oh, this sucks." So if two category theory sucks, then infinity category theory clearly, sucks to the power n for any n. I mean, some people live and breathe it. I find it quite hard. I just kind of have a kind of black spot when it comes to things like simplicial sets and so on, but that's just my failing. But what we can say is actually logic, and in particular various brands of Martin-Löf type theory, are terribly useful, kind of going back the other way. It's not so much explaining logic in terms of category theory, but using the logic as a language, an internal language, to make it easier to talk about high dimensional categories and the relation to homotopy theory. And also to get an account of things like univalence and so on, where there's computational content. So I'm thinking here of the work that Thierry Cochon and his collaborators have done on so-called cubical type theory. So this is a very interesting thing, but it's a story for another time. And so for the moment, that's it. Thank you very much for your attention.
Thank you. Maybe let's try to do the Q&A without the microphone. Let's so speak out loud. You have to say something. Are there questions or comments?
I was sort of confused in the beginning. It seems to me that in classical propositional logic, if something is true for all propositions, then it is true for true and
Yes, yes. So that's this. Maybe it whizzed by a bit too quickly. That's what I was trying to indicate just on the bottom line. Where's it gone? It'll come. Sorry, be there in a moment. Yeah, yes. Here we are. This bottom line here. So in classical logic, that there's no problem with defined quantifiers, because you just instantiate it true and false and take a conjunction or a disjunction.
exactly, but you would
But I think it's
expect an and instead of or.
Yeah.
Oh, did I? Sorry, did I do it the wrong way around?
Yeah.
It's always good to have a typo in your slides. Right? So sorry. Yeah.
Perhaps you were confused very generally, because also all quantifiers are in usual theory smaller than existential quantifiers.
Well, not in my world. Not in my world, they're not. In my world, there's no relationship between the two, really, because you have possibly empty domains. So,
True.
yeah.
But most domains are not empty.
Well, how do you know? No, I'm being facetious. I mean, my attitude to things like that is a kind of utilitarian or pragmatic one. So I care about, say, intuitionistic logic more because it's the appropriate logic for doing things in certain categories. So in those categories, it's not the case that you know that objects are inhabited in the sense of knowing that they have global elements generally. So you have to work with that. Yeah.
Other questions?
I mean, just on the disjunction-conjunction thing, though. I mean, but it is the case, right, that and you look here that when I was talking about disjunction, it's the for all thing is built up as a disjunction of things that you've built up. So you're building up to this biggest thing from below, and the exist is a big conjunction of things that you're getting coming down from above. So that's it. Yeah.
Yeah,
Okay.
I think you
Yeah, I just wanted to remark that last September I was visiting a conference in honor of Pino Rossellini,
Yep.
and there I discussed with Mamuka Yiplatze,
Oh yeah.
who is in the possession of the mysterious last notes of Dita Patanaya.
Yes.
But I don't think he's ever gotten around of analyzing what Dita meant to say.
Yeah. Yeah.
So
Yeah, Peter and I had a meeting with Dito in whenever it was, 2007, and so I have notes of the talk that he gave, and it's very frustrating because it reaches a certain point where you think, yes, right, so now we're going to do it this way. What do you do? And I think he ran out of time or something, so we didn't really nail him down in the way that we should have done. Yeah, you're right though. Mamuka probably does have material that that could be mined.
your conjecture has not been forgotten.
Yeah, but it hasn't been resolved, unfortunately, which is kind of... I mean, I think it's a good conjecture because unlike some conjectures, I don't think actually it's probably in the end that hard. I think it is resolvable. It's just that we need maybe a new insight or something, but I don't... that's a good thing, right? The bad thing is that when you do resolve it, it's not the most earth-shattering fact to know about, but it would still be a good thing to know, right?
So, do you have any idea of, so it's a matter of studying the free Heyting algebra,
Yeah,
and probably free Heyting algebra on infinitely many.
yeah, yeah.
So what would be the relationship between the free Heyting algebra on countably many and on uncountably many?
Oh, I don't know, but that's probably not so important. I think once if you can resolve this for countably many variables, then you're good, right? Because every formula only involves finitely many, so that's not bad. I think the problem is going down the other way. So free Heyting algebras on finitely many generators, well, they're all infinite, apart from the one on no generators. So, but what about finite Heyting algebras? Okay, so that's Stefano Ghilardi's characterization, which builds on, I've forgotten the man's name, but I mean, it's not dissimilar to other analyses, but just rather cleaner. He gets the infinite free Heyting algebra as a filtered colimit of finite Heyting algebras. They're all finite distributive lattice. Every finite distributive lattice is complete, hence is a Heyting algebra. The cool thing is, can you include one in another in a way that it preserves any existing implications? And the answer is you can. And so you take the filtered, the union, as it were, of these finite distributive lattices. Each of them have got enough implications, and their implications that exist are all being preserved as you go up the inclusions. And in the limit, you get something that is not only a distributive lattice, but pick any two things and they're somewhere in the finite chain, got an implication, so then you've got implications everywhere, and it turns out that that's completely free. And so that's the description of the free Heyting algebra, and you could do it on uncountably many generators. It would just be the same sort of thing. So somehow leveraging that fact, so every finite distributive lattice is a complete distributive lattice, has a topos, because every complete Heyting algebra, I mean, we know amongst toposes that complete Heyting algebras certainly have toposes, because you can do sheaves on a complete Heyting algebra, you get truth values of that Heyting algebra. But the filtered colimit involved isn't a filtered colimit of logical functors between toposes, so yeah, so that doesn't, you can't immediately get the answer like that, but maybe something like that is going to work. And that's what he had in mind. It's just I don't quite know how he was going to get the thing to work in the end. Yeah. Yeah. So.
Other questions? Yes, please, there and there.
Thanks for your talk. Also regarding this construction.
Yes, speak loud.
Oh, sorry. Yeah, I'm wondering about this importance of finiteness.
Yeah.
Infiniteness comes into play.
Yeah.
But what happens if you actually assume a notion of universe levels, and assume notion of smallness?
Yeah, I don't know. Maybe. Yeah. So you're suggesting sort of let's go at the negative side a bit more seriously. That would be worth doing. I mentioned another. Sorry, not completely unrelated to that. If I just flick back to here, here's a negative result. I mentioned it. Where is it? Oops, sorry. Far too forward. Yes, there we are. This is an interesting result because we know something about S4 versus toposes, right? So Boolean topos with a distinguished geometric subtopos would give you a model of S4. So this is, I guess, saying that you know, amongst the Boolean toposes equipped with a subtopos, you look at the truth values there, they're probably not going to be all possible models of S4 because of this reason, because they construct here a specific model of S4 which doesn't have uniform interpolation, and yet if it was the truth values of a topos with a given subspace, then it would. So that's a negative result. It's just not the negative result that we want in general, but yeah.
So thanks a lot for your wonderful talk. So it seems like you have an interpretation of second-order proposition logic into first-order proposition logic, intuitionistic.
Yes, that's right, yes.
And it's a bit surprising because second-order proposition logic is undecidable.
Yes.
First-order proposition logic
Is.
So I can't...
That's why I didn't think it could possibly be true.
Yeah.
Right? Yeah.
But how can I match that up? Or is that...
Well, yeah. I mean, the fact that you have the interpretation doesn't help you decide things in second-order logic at all, right? Because it's an incredibly collapsing interpretation. It's a very special. I mean, from the duality point of view, you get that the opposite of the category of finitely presented Heyting algebras is basically a model of first-order intuitionistic logic. So it's the theory of Heyting algebras has a model companion, and that theory is a very special one. So in that theory, for all commutes with disjunction, right? So and that's true here with these quantifiers, right? When you do an AP over a disjunction, it's the disjunction of the for all. So that's a very special property. So it's a very special interpretation. It's not at all general. Yeah.
Yeah, so I just wanted to make a historical remark. So uniform interpolation was independently discovered by Volodya-Shavukov, who worked on the problem of embedding recursively enumerable Magari algebras into the Magari algebra of piano arithmetic. So so the point was, if I remember, so he proved it for Loeb's logic.
Uh-huh.
And so Volodya's proof is very difficult to follow. In his paper, he describes it as a fist fight. And so it's really, you take Kripke models and then you do something, then it doesn't quite work, and then you use something else, and that iterated 5-6 times. So I never really completely understood Volodya's proof, and I think so later Domenico Zambella made a simpler version of Volodya's proof in which the need for uniform interpolation was not present, but that was because he just considered finitely many generators. And I think so Volodya needed the uniform interpolation to do the proof for recursively enumerable Magari algebra on infinitely many generators. And so later I tried to adapt Volodya's proof to prove the result for IPC.
And were you able to?
Using Volodya's Kripke model method, but I couldn't because the fist fight was too much for me, and so only when I completely said
Yeah.
let's start anew. So I discovered the proof that, of which I found out later, that Hilardi and Zawodowski already had it.
Yeah. I mean, there's always a fist fight, it seems, in proving this, but I would say that the least fisticuffs are probably in Sam and Reggio's account of the subject. You still have to get your sleeves rolled up a bit, but yeah.
Yes, please.
Apparently, yes. I mean, I'll probably put them on my webpage at some point as well, but yeah.
Interesting. Yes, please.
Thank you for the talk. I just want to ask a quick question about going in the positive direction of solving this.
Yeah.
Do you know, so some Heyting algebras are known to appear as Heyting algebras. So
yes.
you mentioned like complete ones.
Complete ones, yeah.
Finite,
well, obviously finite ones are complete, yes.
And from what I know, also all Boolean algebras arise in this.
Yes, certainly, yes.
Do you know any other nice class that appears?
Not really, not off the top of my head. I probably did. I may have forgotten, but yeah. I mean, we don't really have a great means of construction of really different sorts of Heyting algebras. That's the problem, and so my sort of straight answer is no, I don't. But yeah. I mean, it's kind of irritating. You feel like, I mean, the Boolean algebra is one. It works because you can, every Boolean algebra is a filtered colimit of finite Boolean algebras, and every finite Boolean algebra you can, is complete, and you can form sheaves on it, and so it's, you get a topos. But the problem is that filtered system of toposes, in that case, are logical functors, and so when you take the colimit, you get a topos again. But with Heyting algebras, it wouldn't be logical functors, and so you wouldn't, it's not that simple.
Precisely because of that. So would that be true for any locally finite Heyting algebra? So for instance, any Gödel algebras are examples?
I don't think so, probably. Yeah.
You don't think?
I don't know. Well, my mind has been corrupted by thinking about univalence and homotopy theory for the last few years, so I've forgotten a lot. I used to know quite a lot about Heyting algebras because I got so frustrated with trying to prove this result, and I think I've probably forgotten most of it. But yeah, I think the problem with the literature is it's actually kind of a bit scattered, and it's very hard to nobody's really, as it were, written the compendious account of. Partly because it's somehow slightly unsatisfying in what we don't know, what we do know. But,
I think we should leave it at this and move to the break, so where you can ask further questions. Let's thank our speaker again.